Okay, so welcome for this session on mathematics and AI. So the first talk is by Moreno Pintore from Sorbonne Université, who speak about volume of fluid method. Okay, so the floor is yours.
Okay, perfect. I am Moreno Pintore, a postdoc in the group of Professor Bruno Depré at Sorbonne University. Since my PhD in Italy, I always worked on hybrid methods, combining machine learning and classical numerical methods to solve PDEs. This is in the same framework. So in particular, we want to solve a fluid dynamics problem, but combining neural networks with the volume of fluid method. So the framework is the following. We have two immiscible fluids that shares a single set of equations, and we want to admit any possible nonlinear change in topology of the distribution between the two fluids. I talk about distributions because the fluids are immiscibles, so we can always see the domain as the union of two or more regions. And this seems pretty abstract, but indeed there are a lot of engineering applications that follow this structure, and so it is a very active research field. In particular, we can see that the first reference is from more than 40 years ago, so it's pretty old, but the field is very active. So for example, the second reference is one published a couple of days ago from another group in our lab at Sorbonne. So there are a lot of methods to solve this problem. One of them is a volume of fluid method, and we want to change the classical scheme by introducing some neural network. I just add some assumptions. They are not required for the method, but it's useful to present them in a simple way. So I assume that there are only two fluids, so let's say fluid A and fluid B. Then we assume that the equation is just a pure transport, so we have a divergence free velocity field that passively advect both the fluids. And finally, we discretize our domain with a Cartesian uniform grid. This is the strongest assumption that is more or less a bit necessary for the method, but a lot of application uses it, so it's not so constraining. So the equation that we consider is the one here for alpha tilde. Alpha tilde is the characteristic function of the fluid A. So in the region where we have a fluid A, it is equal to 1, otherwise it is equal to 0. So it is a discontinuous function, and this is the main issue of the problem that we want to simulate, because of course to simulate the transport of discontinuous functions lead to a lot of instabilities, at least numerically. So this is the exact equation. We want to discretize it in a finite volume fashion. So we have our mesh, and inside each cell we consider the integral mean of the variable alpha tilde, and we denote by alpha this quantity that in the context is always referred to as cell fraction or volume fraction. Then, since we are in a finite volume framework, the idea is that in each cell we have a quantity that is here. You can see my mouse? I think yes. It is alpha n because it's at the time step n. I, j, k are the indices of the cell. So at time n, I have in each cell a given quantity, and to obtain the quantity in the same cell but in the next time step, we consider what we had before, and we sum and subtract all the fluid that goes out from the cell or inside the cell from the neighboring cells. Since we have a Cartesian mesh, the cell is a cube, so we have 6 faces, and these 6 quantities are all the fluxes that goes outside or inside the cell. This is a fully 3D version because I consider all the fluxes together. An approximation that is always used to simplify a bit the problem is to apply a directional splitting approach. So we don't consider all the fluxes together, we just look at the x direction, then the y direction, and then the z direction, and we sum 3 intermediate contributes. But it's more or less the same idea. The key here is that I start from knowing the cell fraction at time n, and the update is based on 2 fluxes that represent the quantity that goes from one cell to the other. Now the key of the VOF method, the volume of fluid method, is the way in which these fluxes are computed. So this is a 2-dimensional representation to understand the idea behind the VOF scheme. So we are in 2D, just for the sake of explanation. We are in 2D. We have a Cartesian grid, so a lot of squares. I wanted to compute the flux going out from a single cell, a single square. So I take my square, and I take a stencil centered in this square. For example, here my square is the central cell, and I take a stencil of 3 by 3. In this region, I have the 2 fluids. So here I have the red fluid and the blue fluid. And the numbers are the cell fractions. So here in the first cell I have 1, because I have 100% of red fluid. Here I have 0, because I have 0% of red fluid. Here in the middle I have intermediate values, because I have some percentage of the red fluid. During the simulation, I don't know the exact distribution, so I don't know the interface between the 2 regions, but I just know these 9 values. And from these 9 values and the local velocity, I can use different formulas to obtain what I have on the right. So here on the right I have colored the portion of fluid that moves from the central cell to the right cell after a time step delta t. And my unknown is the proportion of red fluid that is inside the part that moves. So on the left, all the numbers are in the entire cell, which is the proportion of red fluid. On the right, the proportion is computed only on the fluid that moves from one cell to the other. And this is my unknown. There are a lot of methods inside the VOF family to compute this quantity with different formulas. In our approach that we will denote by VOF-ML, we use a neural network that compute this quantity. So the input will be these 9 values and the local velocity. The output of the network will be this quantity. Then once we have this flux, we can just put it in the previous formulas and use a classical finite volume scheme. So this is an hybrid method. As for any method of this type, we have some pros and cons. The advantage is the fact that once I have my network, the flux computation is very efficient. I just have to evaluate my network. And also the accuracy for nonlinear or non-smooth interfaces is greater than the one with a polynomial or more classical approximation. And the implementation is pretty simple, because it's just an evaluation of a network, and we can use TensorFlow, PyTorch, JAX, or something like that. On the other side, we need a neural network that is accurate enough. We need to train it on a data set that should be representative enough of what I will see during the simulation, and the training may be expensive. Here in these 2 references, I put 2 works where the VOF-ML has been proposed for 2D simulations. Here I will focus on the 3D extensions, mainly on the technical issues that we had to face to extend the model. So first of all, we had to generalize the physical constraints or symmetries that were present in 2D. Then we have to generalize the dataset, and then we also had to train a stable and efficient neural network. And all these problems are related to the fact that we are increasing just by 1 the dimension of the problem, but the geometrical complexity increases in a very important way. Let's start, for example, from the geometrical symmetries. Once more, I start from the 2D visualization because it's a bit easier. So I start from my initial distribution, this one, that is the one that I showed you before. As before, I have with the two colors, the two fluids, and I focus on this region. That is the part of fluid that moves from the central cell to the right cell. To this stencil, I can apply some geometrical transformation. For example, on the left, I apply an horizontal mirroring, and on the right, I apply a vertical mirroring. Which is the difference between these two mirrorings? The difference is the fact that if I apply an horizontal mirroring, like the one on the left, I see that this portion of fluid that was closer to the right cell now is like here, so closer to the left cell. And so it's not anymore the fluid that will go from the central cell to the right one. So I need to recompute my flux from scratch because it is associated with a different portion of fluid. On the right, instead, I apply a vertical transformation. So the portion of fluid that goes from the central to the right cell is upside down, but is exactly the same. So I don't need to recompute the proportion of red fluid over the total of fluid that is moving. So in general, the key properties is that sometimes I can preserve, like on the right, my flux, and sometimes I have to compute it from scratch. This is in 2D. There are not too many symmetries or transformations of a squares. In 3D, the situation is a bit different because given simple two fluid distributions, we have 96 unique distributions. So of course, I cannot consider them one by one, but I need a general strategy. To do so, I don't enter too much into the detail, but we have the set of possible transformations that are 96, and we consider a basis of this set of transformations. And we want to maintain the property of preserving or not preserving the flux. So on the left, you have the bases that change the flux. They are rotation and reflection. On the right, I have the bases that preserve the flux. Once more, I have a rotation, a reflection, and a change of role of the fluids. That means that fluid A becomes fluid B, and vice versa. The idea is that I would like my network to be independent of the transformation. So if I apply a transformation that preserves the flux, I would like that my network predict the same flux. So the idea is that when we have a distribution in our simulation, I apply all the transformation together in a vectorized way that preserve the flux. I evaluate my network in parallel on all of them, and then I average the result. In this way, the result that I get is independent of which distribution I choose because I'm considering all of them. On the other side, the transformation that I used that can modify the flux are just used like a data augmentation approach to enrich the dataset. This is one type of symmetries that we had to incorporate in the method. There are others. Sometimes they are easier. For example, like to avoid negative masses, it is enough to project the flux on this interval. So it's a very immediate transformation. It's not so complicated, but it is important to ensure that the simulation respects physical constraints. Like in this case, we don't want negative masses. And according to the equation, there may be more or less constraints. So it's important to understand the physics behind the equation to enforce the correct properties. Now we focus on the dataset generation. The key philosophy here is that I don't want to have a dataset that is constructed from other simulations. I want a synthetic dataset that is independent even of the equation that I want to solve. The reason is that the WOF information is very local. It is just a stencil of 3 by 3 or 5 by 5 cells. And so when I go into very fine details, it's like I'm linearizing the interface between the two fluids. So I'm not interested in very complicated surfaces, but very often something linear or with an angle or a smooth curve is enough. So for example, in 2D, the interface that were considered were lines, a couple of lines, and circles. And this was enough in 2D to represent meaningful phenomena. In 3D, once more, is a bit more complicated. So instead of 1 or 2 lines, we considered the intersections between 1, 2, or 3 half spaces, or an ellipsoid instead of a circle. The problem here is that these regions are parameterized by much more parameters. So first of all, there is a problem of sampling, because I want to suitably explore the space of regions that can be generated by these interfaces. And we also need to integrate the regions to compute the fluxes and the volume fractions. So we preferred to use a convex-Hall algorithm instead of standard quadrature to have more accuracy. These are some samples of the dataset that we used with planes or with an ellipsoid. Now we can finally talk about the neural network. I think we could use sooner or later convolutional neural networks, but at the moment we restrict ourselves to multi-layer perceptrons. So this is the classical formula of multi-layer perceptrons. The input is the vector with the volume fractions and the local velocity, and the output is the corresponding flux associated with the stencil. To implement the WOF-ML, we mainly need 3 steps. So we need the dataset generation with the interface that I described before. Usually we consider between 10,000 and a million of distributions. Then we need to train the network. And for this, we usually use a combination between Adam and a rescaled BFGS. And the loss for us is just the root mean square error between the flux predicted by the network and the exact flux that we know because we are constructing ourselves the distribution in the dataset. At this point, we have a trained neural network, and we can just use it in a classical finite volume scheme at the place of our previously favored WOF scheme. And in this way, we just change the computation of the flux, but we keep the global structure of the finite volume approach. Couple of numerical results. The first one is the most simple one that one can devise. So we have a domain with an initial distribution that is a sphere without a cube. Inside this region, there is a fluid A. Outside, there is the fluid B. And we consider just a pure translation. So the object is not deformed, it's just translated in the domain. I simulate this phenomenon with 3 methods. Upwind, that is the most used one in CFD. Limited downwind, that is a state-of-the-art solver in the WOF community. And the WOF-ML method. Here on this graph, I have on the x-axis the size of the mesh, so the number of cells in one direction. So when I have 100 here, means that my mesh has 100 times 100 times 100 cells, 1 million in total. The upwind scheme is very, very diffusive, so the accuracy is very bad. For coarse meshes, limited downwind and WOF-ML are more or less equivalent, but when we refine, we see that WOF-ML converges much faster, so it's more accurate. On the right, we have, let's say, a measure of the surface between the two fluids. Since we are just translated, the surface should remain constant, but with the upwind, we have a lot of diffusions, so the interface grows. The other two methods instead are able to keep the surface constant. This is a slightly more complex problem. We have this velocity field that is non-constant anymore, so we are deforming the initial conditions and then returning back to the initial configurations to compute the error. More or less a similar behavior. So the upwind has very poor precision, limited downwind is intermediate, VOFML is the faster to converge and has a better accuracy. On the right, we still see that the upwind is too diffusive, and the limited downwind of VOFML has the initial and final measure of the surface that coincide. This means that the object is deformed, and then is deformed back to the initial position in a good way, because we preserve the size of the interface. To conclude, we presented the VOFML method. In particular, I focused on the three-dimensional extension. We empirically observe that it shows an accelerated convergence with respect to other state-of-the-art methods, and it is also able to reconstruct sharp interfaces that are not too much diffused. As future perspective, we would like to consider more complex physical problems, but still keeping the idea of the synthetic data set independent of the equation. And we would like to investigate the theoretical properties of the method, but this is more complex because already for the VOF scheme it's very difficult to develop good theoretical properties for 2D or 3D cases. So we would like to do it, but we will see it. That's it. Thank you for your attention.
Okay, thank you, Moreno. So we have time for questions. So maybe I can start. So when you do the training, do you train on a single equation, or is it trained on a family of equations? For instance, the parameter alpha, is it fixed or?
We train on a variable alpha. So here, when I generate a lot of distributions. Each distribution is associated with the vector of cell fractions, and to each vector I concatenate the value of the velocity that is local in that cell, and this value is taken randomly in an interval.
But does the neural network know what alpha is used? So is alpha also an input of the neural network?
Yeah, alpha is the input of the neural network because when I have this plot, the portion of fluid that go from one cell to the other is the function of the velocity, of course. And in the simulation, when I have a non-constant velocity, in each cell I have to consider a different...
no, I mean in the input of the neural network you have the value in your cell, but do you also have the alpha? So does the neural network know the alpha, or does it have to guess it or somehow? So when you show your MLP, I guess initially at the first layer you put at the input the value in the grid, but do you also put in the neural network the alpha?
It's just in the input.
Second?
It is just in the input. So the architecture is independent, but in the input we have cell fractions and alpha.
Okay, and if you use your network for another equation, does it work or?
Yes, because at the moment we just test these problems, but in the other papers in 2D they test more complex equations. The idea is that when we have Navier-Stokes or something else, for the part associated with the two distributions, you consider an equation that is always more or less this one. And so you are again in this setting. You don't need the entire equation for the distribution.
Okay, so it also can be applied to other equations.
Yeah.
Okay. So maybe you can speak loud or... Maybe it's safer that I give you the mic. And I can do some exercise.
From what I understood, a main challenge was to incorporate some symmetries in the model, and you showed that you used for some symmetries you did an average of the output of the model, and for other symmetries you used data augmentation. And I was curious if you tried to incorporate these symmetries in the architecture of the model, trying, for example, some equivariant MLPs or group convolutions, and if so, how they performed with the methods that you chose in the end?
We thought about it, but we didn't find a good strategy to do it because there are a lot of different combinations that have to be taken into account. If I remember correctly, on the 96 distributions, we want to average on a bit more than half of them. So they really has a lot of different configurations, and they are not always very easy to implement as architecture level, because sometimes they are permutations in the order of the input vector. Sometimes you really have to change the values, like when you switch the order of the fluids, the volume fractions of one fluid becomes 1 minus the volume fraction of the other fluid, but the velocity remains constant. So there are some mixing in the types of symmetries that we want to consider, and so we didn't find any good architecture that could encode this property that we want. But of course, if we find one, it will be nicer, because we can avoid the parallel evaluation of all the configurations and the average.
Okay, thanks a lot. I think it's time to thank Moreno for his talk.
Thank you.
And to welcome the next speaker, who I guess is Michèle Sebag. Okay, so Michèle is a researcher at CNRS and maybe also INRIA in Orsay. And maybe I wait. And Michèle is going to speak about causal structure learning. So the floor is yours.
Hello? Hello? Yeah. Hello, everyone. This is the second talk in the causalité project. And this is joint work with Shu Yudong, who is here, and our partners from Fujitsu. So I will start by trying to convince you that the causal learning is a thing to do, because you can see that the first level, so this is the causality ladder from Judea Pearl, and you can see that the first level is just, say, mainstream machine learning. You see things and you just have one distribution. You don't change the reality, and then you predict what will happen. But as we all know, we are into machine learning and artificial intelligence to actually to change or hopefully to improve the world, which means that we have to act on this. And then if we act on the world, then the distribution is different. And this is the second level of the causality ladder. You have to design interventions. And of course, you would like to have your interventions to do the right thing and not to pave hell with goodwill. And then something which is even more complicated is the fact that you might want to imagine what could have been, right? So this is the third level of the ladder, because imagining this, what could have been, is a path to actually to design better interventions and to know where you want to go, where you can go. Good. And the bad news is that actually it's much more difficult as you climb the ladder. That is typical under simplifying assumption. The measure of the models that are good for level 2, for instance, is 0. Among the models that are good for level 1, this is 0, right? So here we are. And now what do we do? So as you all know, the Royal Road is the randomized control trials. This is exactly what you imagine when you hope that the drugs in the pharmacy or whatever have been properly tested, right? You take 2 samples of the population and then you see what happens. There are quite some difficulties, technical difficulties, but the main point is that randomized control trials is just not doable in in the general life. You don't have another planet to test your, say, your recommendations about how to improve the climate and all this, right? Not ethical, not doable, or too expensive. Good. So here we are, machine learning is there, with observational causal discovery. So it all starts like a standard machine learning problem. You have variables, okay, and you have data. And what you want is to infer a causal model which looks like this kind of beast here. You would like to know that, for instance, x3 is the effect of x1. And what those circles here stand for is the fact that you know that you don't know everything, right? So the variables, the noise, this is just to measure what you, the known unknowns, so to speak. The fact that you don't know everything, right? And what you get in the end is something which is a functional causal model, where you have the graph, which measures the, represents the, what is an effect and what is a cause. And you have also the causal mechanisms, those Fi here, which tells you how the cause acts. Good. And we have some applications in the past. So, for instance, think of what is the causality, the sense of causality between having a high quality of work, of life at work, and the fact that your company is economically profitable. Okay, you can see that it changes the, for typically the human resources, depending on whether you see, you think that when life is good, then you become profitable, or when life is profitable, then you can afford to be kind. Okay, that kind of thing, or the diet and so on. Good. So here we are. So let's start simple. We are linear here. And we would like to learn basically the graph and the factors here. So you know that xi is a linear combination of the others, its cause, plus noise. Good. And you make assumptions, because without assumptions you can't prove much. You make assumptions that there is no hidden confounders, that is, there is no variables that you ignore, and which is actually a cause for at least two of your observed variables. That's one, okay? And you also want to have your causal graph to be a DAG, no cycles, because if there are cycles, it's much more difficult to design interventions. Okay, so this is what you want. And then the problem is that it's a nightmare. It's a nightmare because it's a combination of algebraic and statistical difficulties. On the algebraic part, if you want to find a DAG, you know, this is exactly the same problem as when you want to find a Bayesian network. So the number of DAG is quite large, I mean exponential. And you also have the fact that you have, as usual, a finite number of samples, in general insufficient. And from these samples, you would like to estimate the causal mechanisms. So you are plenty in the middle of the multiple hypothesis testing, right? So what do we do? So this is a very well-known recipe. You would like to see whether you can apply a divide and conquer approach. Okay, good. So, but the problem you see is that when you are looking at this graph, it's rather difficult to cut into pieces, right? Because you have one variable have effects and themselves have effects and so on. Good. So we build on a well-known result. You have something which is the Markov blanket of a variable. The Markov blanket of a variable is composed of its immediate causes, its immediate effects, and its spouses. That is, the variables like this one, okay, and their spouse. This is very moral. They are spouse because they share a child. Good. And then you can show that actually your Markov blanket is the minimal set of variables that you need in order to predict the center variable, the A here. Because by construction, your variable A is independent of all other variables outside of the Markov blanket, conditionally to the Markov blanket. Okay, very well. And, okay, so that's That's why Markov blanket is such a good idea. And now you have a result due to Low and Bullman that's saying that when you take, okay, remember that you are in a linear setting, when you take the inverse of the covariance matrix of your data, if you see, so this is theta, the precision matrix, then when you see the support of the support of the I line, then you exactly have the Markov blanket. Very well, good. So here we are, and then using this result, using the Markov blankets, we have sub-problems. Of course, they overlap, but let's continue. So you consider a Markov blanket, and now you would like to learn what is the causal graph in this Markov blanket, the subset. Good. So on the good side, you have the fact that now your number of variables is much lower, which means that your ratio between the number of samples and the number of considered variables is much more favorable. Okay. On the bad side, you have the fact that now the assumption of no hidden confounders doesn't hold. Right? You have variables outside of the circle that might act on the variables inside. Bad news. But the main point is that you can consider, you can solve all these sub-problems in parallel. That's what we do. Good. And this is the algorithm. So you see, okay, you divide, very simple. Then you handle the sub-problems. Look, you have a result. You use a causal algorithm from on the shelf, and then you only consider you only consider a subset of the results. This is the full graph, estimated graph. You only consider from this the effect on the cause of the center variable I, right? Just the cross, we shall see. And now the problem is that the partial solutions you get are inconsistent. Too bad. And you see, here you are, right? So because you take only the cross, the effect and the of this, so you have just this, and this. And now the problem is that you see in this subset, in this subproblem, you might say that J is a cause of I. And in the J, you might say that J is nothing to I, or something. How would you solve this problem? Okay. The good point is that you can do the best thing, which is you formalized this reconciliation problem in such a way that you can delegate this reconciliation problem to something which is just built for, okay, by design. You can show that the reconciliation can be formulated as an integer linear programming problem. And then you have very efficient solver that can solve this and solve this fast. Look, you consider, okay, so these now, the Bij and so on, they are not the variables of the initial, they are the variables of your integer linear programming problem. You are saying, I have this variable, and this will take binary. It's 1 if and only if xi is a cause of xj. You have something which is the V structure, you see, you remember the spouse. So here, xi and xj, they are both the parent of xk, right? And now you have the spouse variable, okay, if they are spouse. And now look, you can express the constraint. You say, right, okay, this guy, okay, I is in the Markov blanket of J. So it has to be either a cause or an effect or spouse. Okay, and the problem here, y greater than 1, I can come this if there are questions. You can say, I don't want cycles. Okay, only cycles of length 2. We'll come back to this. And you can say, and this was the main difficulty, you can show that the relationship between the spouse and the cause and effect, you can express this as linear constraint. And you show that actually this is not equivalent, but the true solution satisfies all your constraints. And you show this by looking at the truth table. Good. So now, the conquer step, you have divided, you have the partial solution, you want to conquer. the conquest step is just you try to solve subject to all constraints on the slide before, such that your solution is as aligned as possible with the naive merge from phase 2. That is the sum of your partial solution from phase 2, right? And you just delegate this to Gurobi or another solver. Good. Now, how does it work, right? So you have synthetic benchmarks, you have a real-world benchmark, and your questions are, is it fast? Okay, fast, but also what is the quality? What is the true positive rate? What is the fraction of the two edges that you find? What is the false discovery rate? And what is the structural Hamming distance here, the distance between the graphs? Good. And you would like also to see what happens, because, you know, in phase 1, you divide. What happens if you make errors there? Okay, will the error propagate in the whole thing? Okay, and you would like also to know how the result depends on the algorithm you use in the phase 2 to find the local causal graph. Good. And then this is where we are. So you can see this is on Erdős-Renyi 2, degree 2. And what you can see is that with respect to the true positive rate, with respect to a GES, grid equivalent search from Chickering, you have something which is about the same. About the false discovery rate, you are much better. So see the blue, the difference between the blue and the black, I don't know whether you can see this, because one is we see what happens when you give the ground truth Markov blanket, just to see what is the difference of having an error there. And the best news is this, right? The fact that in log scale, well, you are much faster. With respect to DAGMA, DAGMA is, I'd say, the best causal algorithm so far, in the currently, right? You see that you have a slight loss, very slight, in terms of true positive rate, a slight loss in terms of false discovery rate, because here the lower is the better, and you have a very huge gain in terms of time, computational time. Good. When you are on Moonin, so you remember Moonin, this is something which is related to the muscle disorders. I just realized that I just forgot. So this is a biological problem, and with something like 1,040 variables, you see that here you have the true positive rate, right? And the larger, the best. So here you are the best. And here, regarding the structural Hamming distance, you want to be low. And here, compared to GUS alone, also you are better. You are even better than the DAGMA. Okay, and compared to the time in seconds, so this works using 400 CPUs in parallel on the Ruche, which is another facility from the Paris-Saclay. Well, you can see that, again, in log scale, you have a gain in terms of orders of magnitude. Good. Okay, so the good news is that we can parallelize the search for the causal graph. The good news is that we can delegate a big part of the work to something which is to a framework, computational framework, which is very efficient. And the one point is that you see for each phase 1 division, phase 2 solving, phase 3 reconciliation, you can have a lot of choices, and depending on the problem, you might have an interest in choosing one or the other. Typically, if you have the case for specialists, you might know that when the variance of the noise is not the same for all variables, then the problem becomes much more difficult. And then, depending on that, you might have an advantage to choose GS instead of DAGMA. The limitation, there is a limitation, of course. You can see it doesn't work when you have a very dense graph. Why? Because in this case, the size of the Markov blanket becomes very large. And that way there is no gain in considering a Markov blanket compared to considering all variables. Good. And now what we'd like to do in the future, this is to see, to extend this to nonlinear settings, okay, and typically using the design of the extraction of the Markov blanket based on feature selection. And also something that might be really interesting is the fact that the solver actually returns a host of solutions. So the question is whether we can design an ensemble approach and try to see whether among all those solutions you have something like a backbone. So this is the spirit of the bagging, something, right? And also for a longer term extensions is the fact whether you can say go from ILP to quadratic programming by considering a more complex score function, typically involving the log, approximating the log likelihood. Okay, and now I would like to say thanks to all the co-authors from Fujitsu and first of all for Shu Yodong, who is the one here, the top one. Thank you.
Okay, thanks, Michèle. So we have time for question in the room. Wait for me.
Or I can project. I can shout. Okay. Well, first of all, many thanks for the presentation. I just this is a bit new to me, so I just wanted to ask you a question about the Markov blanket. So I understand that doing all this, we can essentially recover, let's say, the Markov blanket of any node in our causal graph. What is a bit less clear to me is, once we have this information, what can we actually say about the causal graph per se? I mean, can we actually recover it? Can we partially recover it? Can we recover it up to certain equivalence classes? Or how far can we go, basically, from there?
Well, think of it. Assume that we have the Markov blankets, right? So for every node. So we know that each node in the Markov blanket here, each guy here, is either a cause or an effect or spouse. So basically, if we think of this in terms of a combinatorial optimization problem, the size is something like, say, size of the Markov blanket to the cubic, okay, times the number of variables. So, but is it the question you ask? Okay, the answer is, once we have the Markov blanket, this is a step. But the next step, if we are alone with the Markov blankets, the next step is the combinatorial optimization problem, which is nasty.
Well, this is actually my question. Let's say that I have the Markov blankets.
Yeah.
To me, since the Markov blanket contains, as you said, both spouses, children, and children, I cannot tell whether a certain variable is a confounder, whether it is a cause or an effect, just by knowledge of the Markov blankets. And
right.
This is what I'm trying to say, if we can somehow leverage the knowledge of the Markov blankets to go further, and in which classes of graphs we can do that.
Which class of graph? But we are after, not because it's the problem of say in the domain, but because it makes life faster, easier for us. We are into the class of DAG, directed acyclic graphs. And once we have the Markov blankets, then we are not very much advanced toward the DAG.
Okay.
But perhaps we can
yes,
discuss this
after
the record.
Yep. Second question, I just stealing the mic. Oh, sorry. Was there another one? No.
There is another question there. Gabriel, je crois qu'il y a une autre question ici.
Okay.
Pardon.
So one question is, here with your approach, you're separating the nonlinearities from the loss function, from the combinatorial aspect that you solve afterwards in your phase 3.
Yeah.
So with this, can you integrate other losses from, say, Poisson loss or something like this, instead of just the linear world that you presented initially?
This is our next step. At the moment, we are linear, okay, and still, surprisingly, it works on things where the mooning, we have no guarantee that this is linear. But definitely, the next frontier is how to extend this to the nonlinear case. And I think that the main point would be what would make the difference is the fact that we can no longer rely on the precision matrix to find the Markov blanket. We would have to consider something like the, say, feature selection.
Yeah, thank you, Michèle, for the talk. So regarding this slide, if I understand well, the first step is to make a 0-1 decision on the Markov blanket, is there an edge or not, and then to reconcile everything by constraints. And I'm wondering if it's possible to combine this with quantitative criteria, for example, information-based, information theory-based criteria, to give weights to the edges and kind of push around this information in the constraint approach.
You're right, you're right. I mean, actually, you see here, at the moment here, we have this, here, you know, we have the constraints, they are there, and then at the moment we are trying to align this. And this is binary, and this is binary. But perhaps we could extend this to incorporate the fact that we have an information from the phase 2, which is the fact that some edges are more important than others. Mm-hmm. Yeah, you're right.
Okay, but do you already have results in this, or is it work for the future?
Ongoing work.
Okay.
We can discuss about this. Yes, there is. I don't know if Thomas is there, but yes, there is a PhD in the PEPR was working on this.
Okay, so I think it's time to thank Michèle for our talk.
Thank you.
So we need to welcome the next speaker for this session. We welcome Julien Hermant from Bordeaux, from IMB, who is going to speak about optimization, so SDOT.
Hello, hello. Make me a sign if I lose the mic. Okay. So yes, hello. So I'm a PhD student at Institut de Mathématiques de Bordeaux, funded by the PEPR, and I will present a work we've done with another PhD student at my lab and with my advisors. So we'll talk about optimization. Why talking about optimization? Because during the learning process, at some point, you have some optimization problem to tackle. And in some cases, it can be formulated as a minimization problem of a sum of functions that go from RD to R. And in this work that we assume to be differentiable. An important motivation to study this problem is the case of supervised learning, when you have pairs of data, a parametric model, a neural network or linear model, and so on. And in order to learn your model over this training data, you may want to solve this minimization problem that becomes an important part of the learning process. Okay. So, apart from the questions of generalization that are important, but that we did not study in this work, one of the things you want when you study this problem is to solve it efficiently. By efficiently, I mean fast. Although you may have tons of data, so a very large N here, or you may have many parameters in the model, so you're in high dimension. In practice, we solve this using algorithms, and often algorithms that use gradient informations. So there are many, many examples, SGD, Momentum, Madame. And maybe the most basic, the most classic is gradient descent. That is recalled here. And all these algorithms, in general, if you want to use them, you have to tune them. You have to tune here the step size, the sequence Sn. And if I want to minimize this easy 2D function, so I want to find the black cross, which is the minimizer, I know that if I run my gradient descent, if I if my step size is too small, my algorithm will be too slow. If it's too big, my algorithm will hardly converge. And so there is this trade-off of good step size to find in order to have my best possible gradient descent. Okay, gradient descent is considered as rather slow, and popular algorithms such as ADAM incorporate additional mechanisms. One of these important mechanisms is the momentum. The idea being that you had some momentum terms that take into account the distance between the two previous iterates. So here, as for gradient descent, you have to study you have to tune your step size Sn in front of the gradient. But also you have to tune this momentum term that is alpha n there. And so if you take it high, so your trajectory will go very fast to the minimizer. So because of the momentum, it will go up, and maybe too up if you too high if you take high momentum parameters. So we have to take care of this. There are several kinds of momentum algorithm. The one I just introduced to you is polyax-heavy-ball. I guess it is the oldest, maybe. Another important algorithm that also incorporate this momentum mechanism, also in a slightly different way, is the Nesterov accelerated gradient algorithm that I will call NAG. And one of the reasons it is a famous algorithm is that among all algorithms that use gradient information, if you want to minimize some function, classical class of function that is convex with ellipsis gradient, L-smooth function, then this algorithm will have an optimal conversion speed. So it is the best among this algorithm in some sense, which is a rather strong result that make this algorithm interesting. As a side note, so maybe you never saw this algorithm, but maybe you actually did. Maybe you already seen this formulation. Okay, the first formulation that is known in the machine learning community, implemented in Torch. Maybe you know the formulation below, more popular in the optimization community. And these two formulations and others, and actually some algorithms in the literature, are all different formulations of this NAG algorithm. And I will say that sometimes the algorithm literature can be quite confusing because you may have different formulation for the same algorithm, sometimes with different names for each. And worst, at some point, you might be comparing two algorithms that essentially are NAG to the same algorithm. Okay, end of the side note. Let's go back to our problem. We want to minimize a sum of function. So we might want to use our gradient descent or NAG algorithm. Clearly here there is a specificity is that if you want to compute the gradient of your function, you actually have to compute the gradient of each function in your sum, so you have to compute big N gradients, where big N is the size of the dataset intuitively, which can be very high, so it can be really computationally heavy. So in practice, what we like to do is not compute the whole gradient. We like to take some indices between 1 and n, let's say k. We take the associated gradient, we make an average, and it gives us an estimator, delta tilde k here. With that, what we can do is to take your beloved algorithm, such as gradient descent, and replace the gradient with this estimator, which gives you the stochastic version, stochastic gradient descent. You can do the same thing with the Nesterov algorithm, NAG, which gives you its stochastic version, that we call SNAG. And although you're using approximations of your gradient, so you're not having all the information, this algorithm works really well in practice. In particular, the one below, the SNAG, works even better than SGD. So there is this question, why so? And in order to study this algorithm, you want to study this object here. One of the possible approach, so it will be a bit technical here, is to consider the case you have some geometrical properties on your function. So let's say each fi is a Li smooth. Then you can have a bound on the variance of the estimator, which can be split into two terms. So one constant term here, one that depends on x. So x are the parameters of your model intuitively, such that if you go away from your minimizers, this left term will grow higher. Okay. So in this setting, if you wonder if your SGD algorithm makes you converge to the minimum, you have to take step sizes in your algorithm that goes to 0. apart if you use variance relation techniques that I won't mention here. But without further assumption, you have to take step size that goes really small to 0, and then necessarily you will get convergence results that are slower compared to the case where you can keep constant step sizes. And quickly, this is because your algorithm may reach an optimal point for your function, so optimal parameters in some sense, while in the same time, the noise of your gradients may be non-zero, which means that your algorithm won't stop unless you stop it yourself using decreasing step sizes to 0. Okay. Well, in practice, to my knowledge, we hardly take step size that go to 0 because it's too slow. We take constant step size often, and it works quite well. So there is question why so. And I would say that one possible explanation is the concept of interpolation. In the case of supervised learning, it's a case where your model is able to perfectly predict all your training data. So you have this kind of equalities here. In terms of loss, it means that there exist parameters such that your loss is 0. Interestingly, there are empirical theoretical works that tends to show that it will typically occur for over-parameterized model, such as big neural network, or the easy example is a linear model with more parameters than equations. From the optimization point of view, it means that you have this kind of thing that roughly is that there exists a common minimizers for all the function in your sum. And the consequence of this kind of assumption, so I go back to my sum of functions that are all Li smooth. I write again the bound I have on my the variance of my estimator 2 slides ago. Under this interpolation assumption, this constant term here on the right disappears, and this means that in this case, if I approach to my minimizers, the noise of my estimator will go to 0. And this means that I will be able to prove convergence, let's say, of SGD, with constant step sizes, which will give me better convergence results, faster speed. Okay, so now I will clarify what we mean by faster result. Our criterion will be that we'll seek for what I will call epsilon precision. So given an algorithm xn, I will be interested in a bound on the number of iterations I need to wait to be ensured that I will have this kind of inequality, which means that I'm at a distance epsilon of my minimum. So the smaller the epsilon, the more precise will be the solution. And I'll be interested in the smallest possible bound here, which means that I will have a fast algorithm. Okay. So this being said, if I consider gradient descent to minimize some rather gentle functions that are convex L smooth, it is well known that I will reach such solutions in a number of iterations or an amount of time that is roughly 1 over epsilon. Okay. So the smaller the epsilon, the more precise the solution, the longer I will have to wait, which is logical, up to some constant factors that we will ignore. And as I mentioned, the cool fact is that under this interpolation assumption I introduced before, the stochastic version, SGD, will reach this kind of solution roughly in the same amount of time, 1 over epsilon, with different constant factors, but the dependence in terms of epsilon is better. The other thing I mentioned earlier is that if you want to minimize this kind of functions, there is a super cool momentum algorithm, NAG, that will be really better. Its dependence in terms of epsilon is 1 over square root of epsilon, which is really smaller when epsilon is small, when you want precise solution. So now there is a natural question. Under this interpolation assumption, will I have that the stochastic version of this algorithm will have the same kind of speed, such that it will be really faster than SGD? So the answer is not that easy. There exists some negative results in the literature. The first ones here are related to the fact that you can interpret this momentum term here as a term that will induce memory in your algorithm, which is not the case with gradient descent. And when you use stochastic gradients, you make an error compared to the true gradient, and this memory may accumulate this error, which can be hurtful for the convergence. Okay, you also have some lower bounds here that I won't detail, but to sum up, in this context of rather easy convex smooth function, your SNAG algorithm won't be better than SGD. Okay, so your momentum theoretically does not improve. And why? I would say that the thing is that although you are in this interpolation setting, to prove the convergence of this algorithm, you need to have step size that goes to 0 to control this error problem. So necessarily, you have less good speed of convergence compared to this. Okay. Can we overcome this? We know we can, thanks to an assumption on the estimator, which is a strong growth condition. So this is a bound. It is bounded by the square norm of the gradient and some constant factor, rho k, which will act as a noise measurement. The higher it is, the higher the noise, there is noise in the problem. And the striking fact, for this convex smooth function, under this additional assumption on the estimator, your SNAG stochastic momentum algorithm will reach an epsilon solution in a number of iterations, that is 1 over square root of epsilon, exactly what we wanted. And if you look at the constants in the bound, it's exactly the same as for the deterministic counterpart of the algorithm, up to this rho k factor is that acts as a linearly degrading constant. So the more is the noise, the less good is the bond that is okay, logical. So in some sense, this strong growth condition here allows to stabilize the error of the estimator such that you get deterministic-like results. So this is rather cool. You can take this bound, take the bound for SGD, you can compare them, and you can exhibit a criterion over this constant rho k such that if it's small enough, your bound for SNAG are better. Okay, this is interesting, but now there are some questions. One of them is, when will this condition will be verified? And more, when will it be verified such that you may have the intuition that this inequality here will be verified, and so ultimately, such that you have interest of momentum. This was really the core question of our work, characterize this constant here in this condition. There is an existing characterization. So in the case of some functions, strongly convex, each fi is Li smooth, you have interpolation, you know that it will hold this condition for some constant that is there. Okay. Can we have different characterization? Can we have characterization for less restricted functions? Because okay, neural network in general won't verify this. Let's look at a very easy example. We have a sum of two functions, quadratics. E1, E2 are standard basis vectors. It's pretty easy to see, thanks to the previous characterization I just mentioned, that your strong growth condition, your condition will be verified for some constant that is 2L over mu. Okay. On the other hand, you can see simply by developing the square norm of the gradient that your strong growth condition will be verified with a constant that is 2. It means that in this example, you can make move mu and L as you want, such that the ratio L over mu goes arbitrarily large, but at the same time, at worst, it is 2. And I recall that the previous complexity bounds on the number of iteration to wait to have epsilon precision are better as long as rho k is small. So we want it to be small, and in this case, the L over mu can be really, really suboptimal. Okay. So this idea of developing the square norm of the gradient, and in some sense, exploiting the finite sum structure of the problem, allows you to do it in a general case and split it in two terms, one being the noise estimator, what we're interested in, and some terms that you can see as a correlation of your gradient in average. And now you can easily see that if this gradient correlation is positive in average, then your strongest condition will be verified with a constant that is n over k, when n is a number of function and k the batch size. And I will just insist on the fact that this result on here, you do not need assumptions such as convexity or gradient Lipschitz of the functions. Okay, so this assumption is a bit gross here. You wanted to go a step further. reintroduced a condition we named Rakuga. You recognize the average correlation of your gradients, normalized by some terms, but the important information here is that it's lower bounded by some constant C. So it allows so it's an extension of the previous characterization, C equals 0, and it also allows to characterize anti-correlation, C below 0, and correlation, C over 0. And with that, if you have that it holds for some C in R, you will have that your strongest correlation will be verified for some constant that is n over 1 plus 2C. And this will be smaller as long as there is correlation in your gradient. We'll come back to this left. So this is for batch size 1. You can extend it to batch size k with the knowledge of batch size 1. So the bound is a bit ugly and it's a bit technical, so I will skip this. But in the end, if you have that Rakuga hold for some C in R, you have that your strongest correlation will hold for some constant that depends on k, n, and your gradient correlation C. Okay, so you can use it in your complexity bounds. Another thing you can do is to study the impact of increasing batch size on the performance of the algorithm. So, okay, to clarify things, one iteration of gradient descent, or NAG, you need to evaluate big N gradients. One iteration of SGD SNAG with batch size k, you need to evaluate big K gradients. So clearly, one iteration of GD or NAG is N over K more computationally heavy than one iteration of SGD or SNAG. So we'll just change the question we ask. Instead of wondering how many iterations, we'll wonder how many gradient Fi we need to evaluate to reach an epsilon solution, okay, to make comparison between algorithms that don't have the same batch size. This being said, the results, for convex function L smooth, still, if you have strongest correlation with batch size 1, then your SNAG algorithm with batch size k will reach an epsilon solution in an amount of gradient Fi evaluation that is split in two factors, one delta k factors, and one factor that is exactly the number of gradients you need to evaluate to reach an epsilon solution with FSNAG with batch size 1. So this means that this delta k determines if you're making an improvement with this batch size increasing, and if your Rakuga condition holds for some C, your gradient correlation, then your delta k will depend on k, n, and c. Okay. So to sum up what I just said with the hand, the result is if you note perf k is a convergence speed with batch size k, perf k will be delta k perf 1, where delta k depends on the Rakuga constant. So now there is three regimes. If C equals 0, your gradients are orthogonal typically. In this case, delta k you can compute it is 1 for all k. So in your bound, there is no difference with the batch size. In the case where there is correlation, you have C positive. In this case, delta k is increasing, and so small batch will be better. In the opposite case, delta k will be decreasing, and big batch will be better. The intuition behind this is rather easy. So I expected I had a blackboard, but I will do it with the hand. If you're in your space of parameters, you are at some point here. If all your gradients are like that, very correlated, your average gradient will be like this. And you see that taking one gradient instead of taking all your gradients, you won't lose many information. On the other hand, if you're here, like your gradients are really anti-correlated, in some sense your gradient do not agree on the direction to take, your average gradients will be like this. And here it's really more helpful to take one gradient instead of computing all of them. Okay. So you have 2 minutes, so I will go faster. I will quickly show some numerical experiments. There is two. The first one in a very easy case in our regression, because it fits our theoretical setting. And another interesting thing is that it explicitly makes appear the data correlation. So in this case, we can expect a link between data correlation and the performance of the algorithm instead of just gradient correlation and performance of SNAG. So okay, I will go faster here. Okay, so maybe I'll talk on just this experiment. So the top row is an experiment with really low correlation inside the data. The bottom row experiment with high correlation inside the data. The first thing you can see is that if you plot your correlation value, your Rakuga value, it will be really higher in the case of high correlation inside data. And this is what I just mentioned. Okay, if you focus on the top left row, this is conversion speed in terms of gradient evaluations. You can see that your SGD algorithm in black will beat all the run of SNAG, of momentum, in the case of low correlation, which can be reverted in the case of high correlation. There is a second information on this graph. It's a question of deterministic versus stochastic. In the first case, you see that NAG, the deterministic momentum algorithm, completely outperforms all the stochastic algorithm, which can be reverted in the case where there is correlation. Okay, so I guess I'm out of time, so I will skip to the conclusion. I have some experiment on convolutional network. You can discuss them if you want. So the main idea is the question of it's the idea of a link between correlation and the performance of the algorithm. And I will just talk about some perspectives. I just say one. For now, RACOGA is rather a theoretical tool. Okay, it's kind of hard to compute. I believe an interesting thing would be to make it a practical tool, maybe using an estimator, which maybe could be useful to use during the learning process. Okay, and I will leave you with the QR code of our work, and I will say thank you for listening to me.
Okay, thanks for sticking to the time. So it's time for questions. So maybe I have one. If I want n to goes to plus infinity, if I assume like interpolation, here I would have to have k also going to infinity, or? So here, your delta k, it goes to 0 with n, right? This is the problem.
Sorry?
The delta k, so
yes.
The parameter of interest of your method, it goes to 0 if the number of data goes to infinity, right?
Delta k is a batch size. So it can be true.
I mean the parameter,
delta k.
The strong convexity,
sorry.
If you can come back to the...
Yes, absolutely.
So if I want the number of data to goes to infinity, what can I do? Can I just take k to infinity as well, or?
Yes, or the thing, if big N tends to infinity, the complexity grows.
But if I'm a complexity of what?
Yes, no, it depends.
So my question is it possible to extend your theory to having an expectation instead of a finite sum? I don't know.
Yes, it's a good question. But the thing is that I don't know, because all this theory is based on the fact that you can develop the square norm. So you will have some scalar product that appears, and in the case of if you still have an infinite sum, I guess it will work in the same way. I did not think about that actually. But if you really have an expectation, but you will not clearly have a sum, it's here that it absolutely won't work the same way.
I think the problem is that delta k is going to 0, right? If n goes to infinity?
Delta k, yes, with fixed k, yes.
But maybe you could also make k grows, and maybe it could work if the batch size is also growing with n. Or?
Yes. I did not think about that, but it's interesting.
Other questions? Yeah, maybe you can just yell.
Okay. Yes, it would. The question would be to find to weight the iteration such that the mean of your function is okay. Well, I guess in this setting it would be the same. Maybe you can find a different thing if you see it really this way. I don't know. Yes, in general, we use this point of view when we study really non-convex things, because it works this way. Just like that, I would say maybe we would get the same result in this specific case with the convexity, but yeah, I don't know. Yes. Yes. C is lower bounded by 1/2. It's a critical value. Intuitively, the critical value where your gradients are fully anticorrelated. Yes, yes. In our definition, we said it's in R, but you can compute that indeed it's a result that it's low bounded by 1/2. But yeah, we defined it for C in R, but
Perfect.
in practice it will be lower bounded.
Okay, let's thank Hugo for this explanation and for the talk. And now we welcome Hugo for the last talk. So Hugo Leclerc from Paris-Saclay. And of course you have to conclude a mathematical session by optimal transport. So this would be a talk on semi-discrete optimal transport.
So many thanks. So I'm very happy to present you a tool we developed with Quentin Mérigot and Thomas Galouet, notably, to make computations for semi-discrete optimal transport problems. Well, it's a library written in C++ with for no interfaces in Python and C++. It's free software, and you will be able to find easily the sources and some documentation on the net if you want to play with, or let's say to work seriously with. Also, it's possible. Yeah. So I will start with some explanations on what semi-discrete means in our context. I will show some very basic examples. It's a non-exhaustive set of illustration of what we can do with semi-discrete with the semi-discrete setting. Just to understand what happens and what we can expect from this set of this setting, and I will of course speak specifically about the package we're speaking about. Okay, so as I've not seen any presentation during these sessions on optimal transport, if you agree, I will explain one word at a time what semi-discrete optimal transport means. So, sorry for people who already knows every word here. So, transport, the idea of transport, let's say we have two measures, or we can say two functions if we want to speak with simple words. And we want to go from one function to another one just by displacing the mass of some parts of the first function to the second one. We want to move it. We can say horizontally. It's if we say in the unidimensional setting, it's like moving in the x direction. Or if you want to take an analogy, it will be like moving soil in wheelbarrows. If you want to move soil in land, to go to one setting of hills on holes or things like that to another setting. And so I speak about wheelbarrows to explain what do we mean by horizontally. we move the mass horizontally. Okay, so that was for the word transport. For the word optimal is well. The point is that we want to do that by minimizing a cost. If we stay with the analogy of the wheelbarrows, we can say, for example, we would like to minimize the number of wheelbarrows we have to take, or we can say, and it's our case, and we will focus on that for several reasons. We can say that we want to minimize the sum of the square of the length of trajectory, made with the wheelbarrows. So in our case, we are focusing to be more explicit on the quadratic case for the cost. It's for several reasons, notably because we are interested in applications where this cost arises, and also because it exhibits some very interesting properties that we can use to make very fast computations to find what is the optimal transport. So the last word was semi-discrete. Well, semi-discrete means that one of the two measures, or one of the two functions, we want to speak with simple words, has to be a sum of Diracs. And the other one can be more general. It's not the most usual case we see in optimal transport. In a lot of applications we can see, for instance, with deep learning, we see a Dirac, a discrete setting. On one, while we can say here we have a generalization. One of the two measures does not have to be a sum of Dirac. But well, in our case, as we are working with a quadratic cost, we have some very nice properties, leading to very fast computation times. So this is a first example of what we can, why we may be interested by semi-discrete setting. So it's an example of a shape registration example. We start from a point cloud, say for instance for something we have from a machine that gives points for an experimental acquisition, and we want to display those points to something that is not a point cloud. For instance, it can be in surface. So naturally, we would like to use things like semi-discrete settings to do that. Of course, it will be possible to discretize the surface, making points, but it can either lead to accuracy problems, because we have, if we take a too low number of points, or too high computation costs. So it's a natural case where semi-discrete will be used. Okay, this is another example where this one is, I think, already known by a lot of people. It's about optimal quantization. We start from a density. Here I have a very simple example. It's a sum of three Gaussians, and we want we say we have a fixed number of points, and we want to find positions of some point positions, so that each point share the same amount of the density. So this is done very naturally, probably with the semi-discrete setting. Another case where I guess I don't have the time to explain a lot of things about that. Here we show some sample applications where we try to solve PDEs, partial differential equations. You are using different techniques, but the main idea is that we will have a Lagrangian discretization on the direct positions of the Diracs. Will give the discretization of the fields we're looking for, and the other function in the semi-discrete set of function will describe the domain. So it's a fully semi-discrete setting, you can say. Okay. So to speak about the SDOT package, first thing we want to do. Well, because before that, it was already possible to make some semi-discrete optimal transport computations, like for instance using the Seagull package, very impressive and with a lot of possibilities. But we wanted something that is really easy to use, even for mere mortals, I can say non-mathematicians people. But also with possibilities for mathematicians to find all the the usual notations on the same vocabulary than the one we can find in the publications. So I'm not going to explain all the code, but I will emphasize some bullet points. It works in a number of dimensions, provided we want to use a quadratic cost. Also, we spent a lot of time working on ways to play with complex densities. I mean, there are a lot of in the semi-discrete setting. The general measure can be a lot of different things. So we want to be able to play with these different things, like for instance densities discretized on grids, meshes, expressed as analytical functions, combinations of all of that. On all the case to ensure that we are able to make the integration, get the derivatives, and so on. We use symbolic computations and code generations to lead to good computation times. Okay, so we have spent some time to be able to find the derivatives of almost all the outputs with respect to almost of the inputs. I say almost, but well, it can lead to it's enough for a lot of cases. And also, I add that we have specific tools for things like GKO schemes, regularization, partial transport, and so on and so on. Internally, it mainly means that we have to be able to integrate functions that depend on the positions inside the cells, to speak in technical terms. Well, it's mainly about integration and derivations at the end of the day. So it's a word about speed, very important. Crucial, I would say. So we at the beginning we used Seagull on our packages. We tried also other packages to construct the diagrams, but we ended with our specific tools. We construct almost everything in parallel. Meaning that we are really able to use the current hardware capacities. And also it's done in a way that even it can beat the pre-existing software in a lot of cases, even in a sequential setting. So we have some illustration here. And I have to emphasize the fact that the behavior in terms of computation times between versus the number of unknowns is something like big O n log n. It's what can it's something we can see in the middle graph. And also we made some specific optimization for being able to use very few memory. Very few RAM. We also made some specific code for clusters. We have MPI code for a very large number of unknowns, and so on. So, at the end of the day, we can say that it's satisfying in terms of speed compared to what we had before. And I will just end with this slide. Just wanted to say that we use internally power diagrams to find how to solve the problems, and but it's known that power diagrams can be used for a lot of other applications. So we made an API to be able to use all this work on power diagram. It's independent of optimal transport solver, and you will find almost of what is used to be seen for power diagrams, like handling of periodicity, any kind of integrations, and so on. So I guess it's something like no. Ok. Comment le temps, je sais pas. Ah bon, je passe cette info-là. Ok. Okay, so I thought I had something like 7 minutes. It was not the case. Okay. So, okay. No. So I don't have any slides. So I guess if you have questions.
Okay, thank you. So we have time for questions. J'arrive.
Yeah, it's full software. It's available on GitHub. Voilà, this is the URL. Sorry, hard to say. This one.
So
Sorry, what?
I think if you Google SDOT,
okay.
You find it on Google, for instance.
Yeah. You'll find it. It's SDOT /team/SDOT on GitHub.
If you Google SDOT optimal transport, you find it very easily. So I mean, very good job. So I just wanted to say, there are too many want to use it. So maybe a question is, you have a Python interface. Are you planning to have like a PyTorch interface where we could also like backpropagate through the solver, so have the gradient and things like this?
Yes, I would be delighted to do that. I'm expecting some people to say, "Hey, please do that for me," and I will do that with pleasure. I think.
Okay, I think would be a very good.
To add some pressure.
Other questions? Okay, if there's no questions, thanks all the speakers, basically. I think we finish right on time.